Hi everybody. For those of you who don't know me, my name is Jacob Sherba. I'm one of the TFs this semester for Applied Math 21b. My section is normally held Thursday 4:30 to 6 in Maxwell Dworkin 119. But if you look out your window, it is pretty snowy today. The time where my section is supposed to be held is right in the midst of a lot of the storm, and thought that this might be better than having people walk through that. So today we're going to go through the past couple of weeks of material and then also look ahead to what is going to be coming this coming week in order to also help you prep for the midterm on Thursday. So one of the questions I got a lot at office hours was this difference between a number and a scalar. So a lot of you in classes up to this point, myself included, have heard number and scalar synonymously. For this class, Professor Swo is talking about them in a different way. So I want to go through some intuitive things you can think about in order to help make sense of these differences. So a number has a few key properties, and one of those is that it is additive, meaning that if I have two elements in my number field, alpha and beta, if I add them together, the resulting value, let's call it gamma, will also be in the number field F. Now, a number field, and a number, I should say, is also multiplicative. And what this means is that I can multiply some two elements, alpha and beta, together, and some resulting, let's call it delta, will also be in the number field. Now this key point with multiplication is where this concept of numbers and scalars diverge. So a scalar, in the context of this class, is going to be reserved for physical quantities, and we can kind of think of this as a number that has some unit. So for example, if we're talking about, as Professor Swo talks about in lecture, pieces of gold, or number of desks in a classroom, or if we have a set of data that's all in kilograms. All of these have physical meaning attached to them. So scalars as well are additive, where if we have some scalar A and B, the resulting C is also a scalar, is also in the scalar set. However, we do not have this multiplicative property. We have something similar, which I will call scaling, which makes a little bit of intuitive sense because it's a scalar. And what that means is that two elements A times B is not in that scalar set. However, if we scale some piece in the scalar set by a number, say alpha, that resulting alpha times A is still a scalar and thus still in the scalar set. Now, you can almost think of numbers just as dimensionless scalars, where you have some physical quantity, but it doesn't have a physical property attached to it. So we can make sense of this in some ways with, say, multiplying the number 4 and the number 2. We have 8, which is also a number, so it's in the number field. However, if we were dealing with, say, dumbbells, and we had a 5-pound and a 10-pound dumbbell, multiplying dumbbells together would give us dumbbells squared, which in terms of a physical meaning doesn't really represent much. Similarly, we could abstract it one step out and say that we have an array of masses, and we have 5 kilograms and 10 kilograms in a scalar set. We multiply that together and we get 50 kilograms squared, which also doesn't make a ton of intuitive sense. So we are starting to sense this pattern that scalars, when they hold a physical quantity, do not multiply. They can be scaled. I can multiply some 10 kilogram weight by 5, say putting 5 10 kilogram weights in a box, and then I would have 50 kilograms. But in that case, I'm scaling by a number. I'm not multiplying by another scalar. So in the rest of my sections and in office hours, I'll try to make the distinction where multiplication in the traditional sense, where we think of just multiplying two things together, is actually differentiated when we're talking about scalars and numbers, whereby scalars can be scaled but not multiplied with each other, whereas numbers can be multiplied by each other as well as scaled, which an interesting case in numbers is that scaling and multiplication is the same thing because you're just doing the same fundamental operation. Now, we're relating these as a basis of our understanding for the rest of this course. We think of these, though, collectively, numbers and scalars, each being one-dimensional. You can think of, a number line that may contain all real numbers from negative infinity to infinity. You could think of a scalar field that's also a one-dimensional concept, where you have, say, negative 50 gold, where I owe my neighbor 50 pieces of gold, and all the way up to 100 gold, where I have 100 pieces of gold stockpiled somewhere. So there's a continuum on that number line for a scalar, but in both of these cases we have one dimension. This is not the case when we have vectors. Vectors are going to form the basis of a lot of what we do in Applied Math 21b. They are excellent ways, along with matrices, to solve systems of linear equations. And the key difference, one of the many key differences, I should say, between vectors and scalars is that vectors can be n-dimensional. So you could have a one-dimensional vector where I have just one element. So this vector is just the number 8 inside brackets. Let me move this closer for the rest so you can see a little better. That's really terrible. Let's try a different marker. Yeah, that's marginally better. Yeah, that lighting is not better either. Anyway, I'll post my notes in conjunction with this so you can kind of follow along with what's being written down, because it's a little challenging to try and see everything on the board. I'll try to write down here where the lighting appears to be a little better. But vectors, much like numbers and scalars, have different properties. Vectors are additive. So if we have some vector u and some vector v in a vector space, the resulting vector, we'll call it w, is also in that space. Similarly, we can scale a vector. So we have some number c that scales a vector u, and this new vector cu is also there. Now, we can't always multiply vectors, which is just a byproduct of the rules of matrix multiplication. If you remember, if you've had matrix multiplication before, so we have a 3x1 and a 2x1 matrix, we can't multiply these together because their inner dimensions don't agree when we set this up. We could multiply a 3x1 by 1/3 because these inner dimensions agree, and we'd end up with a 3x3 matrix. But if we're dealing, let's say, in a vector space that is simply along the line given by the vector 4, 5, 1, I can't really multiply this by another 3x1 vector because a 3 by 1 vector, as we just saw, multiplied by itself has inner dimensions that don't agree. So in the same way that we can think of scalars as being scalable but not multiplicative, so too can we think of vectors as not necessarily being able to be multiplied by each other, but we can certainly scale them by numbers. So getting a little bit of the flavor of what vectors are, I'd like to go through a few examples. Use the Professor Swo adage that we don't become good citizens by reading legal documents, so we'll go through a few examples and see if we can't pick up some things, and then extract what we can in terms of theorem and whatnot from there. So first thing I want to do is look at vector equations. So what you saw me write before was some u plus v equals w. So this is a perfectly valid vector equation. I denote the vector with these little arrows to denote that it's a vector made up of multiple elements. However, this doesn't really tell us a lot about what's actually going on inside. So let's say I have some vector u that I define as 2, 1, vector v that I have as 3, 4, and then we can simply add the elements together in vector addition. So I have 2 plus 3, I have 1 plus 4 here, and I get the vector 5, 5, which could also represent just as 5 times the vector 1, 1. Now, an important piece of vocabulary to know here is that when you have a vector that only has one column, regardless of how many elements it has, so this only has 2 elements, 2 and 1, but because it only has one column, we call it a column vector. And we'll use those a lot in this class, especially in linear systems. So we've seen one example of vector addition. Let's do another one. Here we have u plus v again, equal to some vector w. In this case, we're going to say that our vector u is 3, 4. Our vector w, or excuse me, our vector v is -1, 2. And we can add these together. Again, we have 3 minus 1, we have 4 plus 2, which gives us 2, 6. And again, we can write that as 2 times the vector 1, 3. Now, as we're talking about multi-dimensional space versus numbers and scalars, which are in one dimension, we can talk about notating these different spaces. So we see that these vectors u and v, as well as the vector w, have 2 elements, and we say that these exist in R2. And essentially what this means is just our traditional x, y axis. Representing this graphically, we could say, we have 1, 2, 3, and then 1, 2, 3, 4. So this would be our vector u, and then we have our vector -1, 2, which is our vector v. And we can actually graphically add these as well. So if we imagine taking this arrow, v, and moving it up to the tip, or the arrowhead, I should say, of u, and kind of sketch out what that would look like, very roughly, we get something that pretty closely approximates 2, 1, 2, 3, 4, 5, 6. So we see that we're not just adding numbers in these brackets, but what we're doing actually has some graphical representation as well. Now this is a very basic vector in 2 dimensions, or in R2, because it has 2 elements. Of course we can go to R3, and as I mentioned earlier, a vector can have up to n dimensions. So you could have a 352 element vector, in which case the space that would exist in would be R352. Visualizing that is something that I would not be able to do. If you can, kudos to you. But really what we can visualize as humans is up to R3, so three-dimensional space. Now, as I mentioned before, we can scale vectors by numbers. So we're going to do an example of combining vector scaling with vector addition. So now we're going to define our u vector to be 1, -2, our v vector to be 2, -5, and let's say we want to have the vector equation 4u minus 3v. So we want to scale the vector u by the number 4 and scale the vector v by the number 3, and then we're going to do this subtraction of a scaled v from the scaled u. So our scaling is pretty simple to see. 4 times 1 is just 4, so our first element in our scaled u is 4. We have 4 times -2, so -8. And let's throw our minus sign right here. 3 times 2 is 6. 3 times -5 is -15. And then just as before, we can add these together, sort out our elements. We have 4 minus 6. We have -8 minus a -15, so -8 plus 15. So our answer for this ends up being -2, 7. And this is just an example of how we can not only add vectors and not only scale vectors, but also do the two of them together. And I'll reiterate that it's okay to scale vectors, but multiplying vectors does not always work in the sense that I could take, u and just do 1, -2, 1, -2. We're going to get to some operations later called the dot product and cross product that are going to allow us to work with vectors in a multiplicative sense, but as far as just basic multiplication of two vectors multiplied by each other in conventional sense is not necessarily legal. So all the examples we've done are with two-dimensional vectors, vectors in R2. An example of a vector in R3 might be the vector 1, 4, 3, and say some vector in Rn would have elements x1, x2, all the way down to xn. So again, both of these are column vectors because we have just one column in each. This has 3 elements, this has n elements, but both are column vectors. Now, like I said, we're going to abstract back a little bit and pull some of the properties of vectors out from the examples that we've done. So, properties of vectors. It's important to memorize these, but you'll find that you memorize them very quickly because you'll be using them frequently in your homework problems. So, property 1, u plus v is equal to v plus u. So much like regular addition, it doesn't matter which order we add our vectors. Property 2, u plus v in parentheses plus w is equal to u plus in parentheses v plus w. So you can think about it as just being able to associate different vectors in addition together. Property 3, u plus the 0 vector equals the 0 vector plus u, which is simply u. So we see a reiteration of property 1. The 0 vector is simply a vector of whatever dimension you're working in, completely filled with zeros. So say the 0 vector in R3 is simply 0, 0, 0. So this is similar to an additive identity saying that some number alpha plus 0 is just alpha. So it's a nice identity property. And you can have a 0 vector of any dimension. Like I said, it's just a matrix or a vector completely filled with zeros. All right, moving on, property 4, u plus negative u is equal to negative u plus u, which is just the 0 vector. So again, we can see that we can add in any order, and this is just adding a vector to its opposite. So say we had vector 4, 3 minus, or I should say plus negative u to use the terminology of the property, so plus negative 4, negative 3, pretty clear that we get 0, 0, and this is just the 0 vector in R2. Obviously not able to raise hands and answer questions, or raise hands and ask questions with this method of filming, but please do email me. My email is on the course website if you have questions. Moving on to property 5, we see that we can distribute a scaling number. So we have c times, in parentheses, u plus v. This is equal to cu plus cuv. So just like with regular numbers, we can distribute a scaling factor across parentheses. And kind of a natural extension of that is property 6, which is c plus d, both numbers, times the vector u equals cu plus cd, or excuse me, cu plus du. So this is just showing that you can distribute the vector across the parentheses when you're dealing with numbers inside parentheses. Again, if we had some vector v in here, we couldn't multiply u times v in the traditional sense. But with numbers, it's fine. And finally, property 7 says that some number c times the quantity d times u is equal to cd multiplied by each other and then multiplied by u. So all these should look very familiar. They're all very similar to regular arithmetic properties and basic algebra properties. We're just extending it to apply to vectors for our properties, or for our purposes here. Now, these properties, as I mentioned earlier, are going to be very helpful in helping us solve systems of linear equations, which we haven't gotten to yet, but I want to make sure that we have the foundational knowledge in order to be able to work with them later. Another key piece of terminology is something called a linear combination. We'll see this come up again and again. So let's say we have some vector y, and it's equal to c1 c1 v1, c2 v2, c3 v3. And in this case, c1, c2, and c3 are all numbers, so we're just scaling these vectors by numbers. And v1, v2, v3 are all vectors. They are the same dimensions as y. So if y is a 3 by 1 vector, then v1, v2, and v3 each have to be 3 by 1 vectors as well. Because all we're doing is scaling these and adding them together. It wouldn't make sense to add a 2 by 2 vector to a 3 by 1 vector because the elements wouldn't match up, so addition wouldn't work very well. But all we're doing is scaling by numbers. And when we do this and add those pieces together, we have what's called a linear combination. So linear in the sense that we are simply scaling. We see these factors here, then combination, adding them together. So it's fairly basic intuitively to understand what that means, but it's a concept that will be very important as we move on through the course. Now, a concept that came up in office hours as well as on this first homework, but we haven't touched on too much yet, is the idea of span. And I think the best way to do this is to draw pictures to help convince yourself. So I'll try to draw some graphical representations that I hope will help this concept to solidify a little bit intuitively for you. But first and foremost, a span is simply the area in space that can be reached by a certain vector. So let's start in 2 dimensions. We have our xy plane, and say we have the vector u, which is 2, 1, which would just be this vector here. So we have the point 2, 1, we have an arrow starting at the origin and going towards our point 2, 1. So we match up the vector notation with this graphical representation. But what's the span of this vector? If we were to draw a line, that's not at all in line with that. If we were to draw a line extending through this, we would say that this line is the span of the vector 2, 1. And it seems a little confusing at first, but it makes some sense if you give it some thought. For example, I could scale this vector 2, 1 by -1, and I would then get the vector -2, -1, which would put me right here at -2, -1. I could scale by -2 and then get the vector that goes to -4, -2, maybe somewhere out here. And you can quickly see how I can go in either direction, positive or negative, scaling by any real number and just stretching this vector along this line. Now it's important to know that with just this one vector, I can't really go off this line, at least dealing with scaling with real numbers. Because no matter what I multiply by, it's just going to be some factor, either positive or negative, of my original vector. There's nothing I can multiply this by in terms of real numbers that's going to give me a vector here. However, if I have 2 vectors in R2, say I have, same as before, the vector 2, 1 and the vector 1, 3. Now I have 2 vectors to work with, and I can start making linear combinations of these. So I could have a vector y that's equal to c1, let's call this v and this u. c1 times u plus c2 times v. And all of a sudden I can start stretching and scaling not just along this line, but along this line as well. And the really interesting thing that can happen when I have linear combinations of 2 vectors like this is I can actually get a span that's not a line, but a plane, which makes some sense. You start to see that, okay, I could take a little factor of this vector 1, 3 and go here to reach this point, or I could take a big negative factor of 2, 1 and end up way over here, and then take a big factor of 1, 3 and end up here. These two vectors are special in that they are linearly independent. What that means is that they can't be written in terms of each other. So I can't multiply 1, 3 by anything and get 2, 1. Similarly, I can't multiply 2, 1 by anything and get 1, 3. So linearly, if I'm just scaling with real numbers, these things are independent. And in R2, if I have two linearly independent vectors, my span is all of R2. We started to see that here, where by arbitrarily picking our points, we can reach pretty much anywhere in the entire xy plane in 2 dimensions. So the span is really just the area, as I said, that you can reach with vectors. Now, with one vector, the maximum you can reach is a line. With 2 vectors, you can reach a plane. With 3 vectors, you could reach some 3-dimensional vector space. And then 4 vectors, 5 vectors, again, it becomes harder to visualize because, again, as humans, we really only have the ability to meaningfully visualize up to 3 dimensions. So I hope that this gives you some intuitive understanding of what span is with vectors. And we're going to move from vectors to a somewhat similar concept in matrices. And we have the matrix equation. You'll see this 100 times in this class, where we have some matrix A, some vector x that has our variables, and then some answer, our b vector. Writing this out, our a vector is really, or a matrix, excuse me, is really just a combination of column vectors. So what we get, this is the same as, say, A11, A12, A13, A21, A22, A23, etc., etc. And then our x vector is simply a column vector x1, x2, up through xn. So let's check our dimensions, because as we said, we should be able to multiply these two things together if the inner dimensions agree. So A is some m by n matrix. X is an n by 1 column vector, which leaves us with B. We see that n and n agree, they're the same, so we're good there. And our outer dimensions give us the dimensions of our answer. So we see that B is going to be an m by 1 column vector. So not even knowing too much about the matrix equation, we see that just using simple properties of vector and matrix multiplication, we can start to discern some information about how this whole thing is going to look. So that's obviously the general case, but this is, of course, applied math, so let's see if we can't do a concrete example. So let's say our matrix A is 1, 2, negative 1, 0, negative 5, 3. So our dimension here is 2 by 3, 2 by 3. Our x vector is 4, 3, 7. So here we have a 3 by 1 column vector. Now if we use, again, our dimensions, we have a 2 by 3 times a 3 by 1. These agree. So we we should have a B that is a 2 by 1 column vector as our answer. So let's see if that works out. Multiplying this through, we essentially want to take each of these individual elements and multiply them by the columns of A. So we're going to have 4 times 1, 0 plus 3 times 2, negative 5 plus 7 times negative 1, 3. We'll scale each of these. So we have 4, 0 plus 6, negative 15 plus negative 7, 21. We'll add these together now because this is just, you see, a linear combination of these. So we have 4 plus 6 minus 7, 0 minus 15 plus 21. And our answer is indeed a 2 by 1 vector. We have 10 minus 7, which is 3. We have negative 15 plus 21, which is 6. So we could rewrite this as rewrite this as 3 times the vector 1, 2. And this is our answer for B. Either this answer or this answer is correct. They're exactly the same mathematically, so whichever one you prefer in terms of writing is up to you. I prefer this. It's a little, in my mind, a little more simplified. Shows you exactly, the most basic vector being scaled. Again, giving you an idea of how that might look in a span. But this is the basic mechanics of how you would go through to do the math of a matrix equation. Now, in terms of matrix equations, we again have a few properties. We have the property that our matrix equation AX plus B always has a solution if and only if B is a linear combination of the columns in the matrix A. And that's what we saw as we were solving that and going in at the end and adding these things together. Now, a few other properties that are mutually true, which essentially means that if one of them is true, then they're all true, which can be really helpful if you're doing a proof or have a question on an exam that has similar true-false questions. So say we have a matrix A, which is an M by N matrix. Our 4 mutually true or logically equivalent properties are that for each B in Rn, Ax equals B has a solution. Each B in Rm is a linear combination of the columns in A. Equivalently, the columns of A span span Rm, and A has a pivot in every row. So these are properties of the general matrix equation. Now, if we're talking about a homogeneous equation, which is a special subset of the matrix equation, where b equals 0, so we have a times x equals the 0 vector. This homogeneous equation has a non-trivial solution if and only if the equation has at least one free variable. So this is going to be important later on in the course. We'll learn some important corollaries to it. Just to really make clear, non-trivial solution means that our x vector is not just a column of zeros. That would just be 0 times everything, which is the trivial solution, because that would give us 0 no matter what a is. So we want to find something that is not all zeros, which we call the non-trivial solution. So, last example I want to do today is an exercise of taking a system of linear equations, translating it to a matrix, and then determining a solution. So, for example, 3x1 plus 5x2 minus 4x3 equals 0. Negative 3x1 minus 2x2 plus 4x3 equals 0. 6x1 plus x2 minus 8x3 equals 0. Okay, so let's throw this into a matrix. We have 3, 5, negative 4, negative 3, negative 2, 4, 6, 1, negative 8, times a vector x1, x2, x3 equals 0. So what we see is we have a homogeneous equation because we have a times a vector x equals the 0 vector in R3. We have 3 elements here, so we have we're existing in R3 for this problem. Now we'll rewrite this as an augmented matrix. So just throw the zeros here. And everyone's favorite afternoon activity is, of course, row reduction. So we will add row 1 to row 2. So row 1 stays the same, 3, 5, negative 4, 0. Row 2 becomes 0, 3, 0, 0. And we'll subtract 2 of row 1 from row 3. So we end up with 0, 1 minus 10 is negative 9. And then negative 8 minus negative 8 is just 0. And then, of course, we have 0 in the last column as well. So this cleaned up for us pretty quickly, pretty nicely. Now we're going to add 3 of row 2 to row 3. So 3, 5, negative 4, 0, 0, 3, 0, 0, 0, 0, 0, 0. Okay. Now, I'll spare you the last algebra steps. We would divide this row by 3, and then subtract it from this first row, a factor of 5 from that row to get rid of the 5 here, and then we would still have that hanging over. To get it in row reduced echelon form, we would divide this row by 3 then, so our final row reduced matrix is going to be 1, 0, negative 4/3, 0, 0, 1, 0, 0, 0, 0, 0, 0. So one of the first things we notice is that we have this guy hanging out here. We don't have a pivot in every column. We have this negative 4/3 here as opposed to, say, here, where we could get it in a nice diagonal line of 1s. And what that is, that negative 4/3, is representative of the fact that x3 is actually a free variable, which means that we can really make it whatever we want, and our answer will depend on it. So we take this then, and we see that if we multiply this by our x vector, we get that our x vector is x1, x2, x3, which we can just read off right from here. Or excuse me, skipped a step. We can read off from here with the augmented matrix still here, a system of equations. We have x1 plus 0 times x2 minus 4/3 x3 equals 0. Here we have 0x1 plus 1 times x2 plus 0x3 equals 0. And that's really all the information we have. But we can rewrite this in a vector. Apologize for the skipped step there. So we have our x vector, which is x1, x2, x3. We can solve for x1 up here. Say that x1 is equal to 4/3 x3. So we have 4/3 x3, x2 is 0, x3, it's a free variable, it's just x3. And then similarly to what we saw earlier, we can factor out an x3 here. And we have 4/3, 0, 1. And this is our answer to our homogeneous matrix equation. And what this means is that we don't have simply one unique solution, but we instead have many solutions, because any scaled factor of 4/3, 0, 1 is going to be a solution of our homogeneous equation. Now, that's an important ramification that we'll get to later in the course, whereby if we have a free variable, that almost always, if not always, means that you're going to have more than one solution, because your vector is not going to be unique, but it's going to be dependent on whatever you choose for your free variable, or sometimes free variables. You can have more than one. Now that process is pretty standard. One of the nice things about linear algebra is that in a lot of things you can really just break it down into a nice algorithm. So the algorithm for solving these homogeneous equations is first to row reduce your augmented matrix. And then you're going to, after you've done that, like we just did, we're going to write each variable in terms of the free variable. Then we're going to write out our x vector explicitly. And finally, we're going to factor out the free variables. Such that we just get a vector scaled by the free variable, which is, of course, our choice. Now, we've gone through today some basic ideas of numbers versus scalars versus vectors, gone through some more nitty-gritty in terms of defining vector properties, scaling and adding vectors. We've gone through matrix equations, both homogeneous and non-homogeneous, talked about span. Next time, we'll get more into the applications of these tools, how we can use them to solve problems with many variables quickly. If you have questions, like I said, email me. My email is on the course website, and I'd be happy to answer any questions you have. Thanks, stay warm, stay dry, and have a good weekend.